determinant of minus lambda, 1, minus 3, 4 minus lambda. All right, expanding that particular equation, we're of course going to get a lambda squared from the diagonal. Also from the diagonal, what do we get? Plus 4 lambda. All right, minus 4 lambda. And then what do we get as far as the constant term?
0.
Plus 3.
From the off diagonal, we get the plus 3. Okay? Can anybody factor this for me?
Lambda minus 3, lambda minus 1.
Okay, lambda minus 3, lambda minus 1. All right? Okay. So, what we get here is we get eigenvalues, well, we're going to say, let's go ahead and get this for lambda 1 equaling, let's say 1, all right? Then our eigenvector associated with that. Okay. Notice what we're doing there. We're going to get, putting in 1, we're going to get minus 1, 1, minus 3, 3. All right? I'll go ahead and put this over here. We're solving minus 1, 1, minus 3, 3, exceed 1 equaling the 0 vector.
1.
So a good eigenvector there is 1, 1. Okay? Now let's do for lambda 2 equaling lambda 2 equaling 3. All right, putting that 3 in here. We're going to be solving minus 3, 1, minus 3, 1, exceed 2 is equal to 0. All right, so an associated eigenvector with that would be
1, 3.
1, 3. I love the way you did that because this is exactly what happens with companion matrices. The nice thing about this companion matrix, by the way, this will relate very much to when we describe what happens between two-dimensional second-order linear equations and first-order systems. So so we're basically saying that x1 dot equals x2. And then we can transform this into you get x1 double dot, and what's going to happen here is, notice these coefficients, how they relate to the characteristic equation. That's the negative of the constant term. That's the negative of the midterm there. And look at the eigenvalues. Eigenvalue is going to be 1 with the eigenvalue here, 1 with the eigenvalue there. This will always happen for companion matrices. The companion matrix is basically 0, 1 in the upper row, something else in the bottom. Okay? So that makes it nicer, easier to do. Okay, we got all this, of course, general solution. Just erase this here. We're going to then say the general solution, x of t is going to be equal to c1, 1 e to the t, plus c2, 1, 3 e to the 3t there. And so now let's draw a pretty phase portrait for this. There again is my x1, there is my x2. Equilibrium again at 0. So we'll first draw 1, 1 goes where? Well, it goes like that, doesn't it? Oops, I should have zapped in the other direction rather than this one. That. And what about behavior along that eigenvector? Solutions go out, exponentially growing, don't they?
Yeah.
So we would put our arrows going out over here. Let me go ahead and, for sake of making it easier for us to see, this is the lambda 1 equaling 1 for that growth. Okay? Now the other eigenvector, we move 1 in the x direction, 3 in the y direction, basically. So we're going to have, let's put a very steep one right here. What about the direction of the arrows on this one? They're also going out. All right, so this is my lambda 2 equals 3, so we have these exponential growths here. Okay. And now, for long-term behavior, what should it look like? Which of these things, which of those are going to dominate?
The 3T.
The 3t grows much faster than the 1t, right? So that says that the predominant direction should be parallel to this one. So if we want to go sort of backwards in time, we're going to start by going parallel to this one and then come in along the other one.
Why though?
Why? Because it's growing faster in this direction. You agree e to the 3t grows faster than e to the t. That's all it's saying. It's just saying this one's is going faster. Yes?
So if if the value of lambda is positive, it goes away from the origin. And
Correct.
if it's negative, it goes towards the origin.
Correct.
Okay.
And does anybody have a guess as to what this might be called? If the other one was called a stable node,
Unstable.
how about an unstable node? Very, very difficult to decide what this is called. All right. And does everybody sort of see now that you get dominant behaviors in there based on the dominant eigenvalue? That's going to do the predominant behavior of what's going on. All right. Everything fine with that. So the slides just go through doing exactly what I just got through doing. And there again, see, and this sort of helps you as you get further from the origin, the direction of the flow should be going along with the largest eigenvalue. All right? And that kind of helps you sort of, you go there, and if you look backwards in time, what's decaying most slowly? Most slowly is going to be the lower one, so that's why you come back along the other eigenvector. These do show forward and backwards in time. Solution does exist for minus infinity to infinity. And in particular, as t goes to minus infinity, this goes back to the origin, doesn't it? Necessarily, because t minus infinity, both of those decay. Okay, let's try another example.